Welcome to those of you who have never been with us, and welcome back to those who have followed us throughout this month, the Bamboo Industry Month. Today is the last webinar of this series on the technologies developed by the Bamboo Project. The Bamboo Project, I remind you, is a project funded by the European Union that aims to make heavy industry more sustainable through the new technologies that we have explored in this webinar series. Today we are going to learn everything about a virtual battery model applied to a use case from the pulp and paper sector. So first of all, let me remind you of the rules. Please keep your microphones and the cameras switched off, and please ask your questions by writing them down in the chat box, which you should see on the right side or the left side of your screen. And you can do so at any time. Don't wait for the end of the presentations. I also remind you that this webinar is being recorded so that it will be possible to access it in the future. You will receive a link to watch it in the following days on the YouTube page of the Bamboo Project. So now let's go through our schedule for the next hour and a half. If you have attended one or more of our previous webinars, you know we propose polls to the audience in order to know you better and make you participate actively in the event. So after this introduction, there will be a first round of polls. Then Jorge Arroyo and Álvaro Pucharoman from Fundación Tirso will present the Bamboo Project, its objectives, its technologies, the technologies that it is developing. We will then go through another session of polls, after which Kilian Dickel from the Technische Universität Braunschweig and Sophie Knöttner, from the Austrian Institute of Technology will show us a virtual battery concept where the plant and the operation of its energy production and consumption assets act as a virtual battery for the local grid. This time we will have another session of polls after the first part of the presentation, so be ready to answer. And we will close this webinar with the questions from the audience as usual. So let's start with a few questions to learn a little bit about you. So let's see the first poll. What do you expect from this webinar? Do you expect to learn about standards and regulations, maybe in your sector, to learn about efficient technologies for your company, to learn about projects of similar companies, or are you looking forward to networking with the companies and share similarities and solutions? We will wait for a few seconds so that you have the time to answer. Here are the results. So most of you, almost all of you, want to learn about efficient technologies for your company, and a few of you, 20%, wish to learn about standards and regulations. That's quite interesting. So good. Let's go through the second poll. Here we ask you to select your area of work. Are you in the paper industry? Are you in the steel and iron industry? Are you in the mineral industry, in the petrochemical industry, or in another sector? It's interesting because we are going to talk of the paper industry, but if I understand well, these applications are also good for other sectors. So let's see the results. Most of you are from other sectors, and 10% are from the petrochemical industry. As I said, you don't need to be in the paper industry to profit from this webinar. So let's go with the Last poll of this round. Let's learn a little bit what you do in your company. Are you in R&D? Are you a technician? Are you in maintenance, in management, or in another role? So again, a few seconds to answer. I don't see the results. Okay. So half of you are in management, 40% are in R&D, and 10% are in other roles. Very interesting. Thank you, everybody, for your participation. Now it's time to give the floor to the first panelists, Jorge Arroyo and Álvaro Pecharoman from Fundación Circe, who will tell us more about the Bamboo Project, which organizes this series of webinars. I ask the other panelists to keep their cameras and microphones off. So please, Jorge and Álvaro, tell us all about this project.
Thank you, Selena, for welcoming and host this webinar. First of all, I would like to say thank you to all the people that are connected to this webinar and are follow the webinar series. And second one, I would like to say thank you to Selena and the ICON teams for the great work hosting this webinar series. That is the last one, and I would like to say thank you to the people that participate and for sure all the participants that make a great job during this month. So, Bamboo Project is a H2020 project. The name of the project is Bamboo. That means boosting new approach for feasibility management by optimization process of gas and waste use. This is an inspired project that started in 2018. This is an innovation action funding by the European Commission with almost 11 millions. They have a duration of 44 months, and this will be finished by February of 2023. You will know more about the incoming events that we are preparing to finalize the project, and so all the advance on all the achievement that we get in Bamboo Project in the following months. This project is coordinated by Circe. They have the project have 19 partners. They are very different partners. We have small and medium companies. We have big companies and some researching centers and university including in the consortium. And this project helped to achieve the OSD from the UN, number 7 and 9. So I would like to introduce to Jorge Arroyo, who is the technical project manager, and he's gonna take a more technical point of view of our Bamboo project.
Thank you, Álvaro, and good afternoon, everybody. Thank you for being connected today. The Bamboo project main objective is the development of technologies which help industries, especially energy-intensive industries, to reduce these energy costs between 15 to 20%, reducing the greenhouse emission until the 23%, and improving the energy efficiency until the 20%. In this sense, in Bamboo, we are working in 3 innovation pillars: the waste heat recovery, electrical flexibility, and waste stream valorization. We are working on the demonstration of these technologies in 4 energy-intensive industry sectors: steel, petrochemical, minerals, and pulp and paper sector. The first pillar is the waste heat recovery. In Bamboo, we demonstrate technologies to valorize the waste stream which have a valuable energy content associated to the temperature of these streams, and allowing the introducing that energy again in the process. In this sense, we have two demonstrators of the steel sector, ArcelorMittal, and petrochemical the petrochemical company Tupras. In ArcelorMittal, we are demonstrating how high temperature heat pumps can help to upgrade low to medium grade waste heat to higher temperatures. In this case, we are recovering energy from some waste stream and use this energy with a high temperature heat pump to generate steam, which can be introduced in the process. This have a direct reduction in the energy consumption, since part of the gas natural used in the boilers to generate this steam is replaced by the energy captured by the heat pump. In the case of the petrochemical sector, we are using overseas to valorize medium grade waste heat coming from a distillation unit, and use this heat to produce electricity, which can be used in the own plant. So this helps to reduce the electric consumption from the grid. The second pillar is the electrical flexibility, which includes technologies and operational strategies that make possible that industries take advantage of the lower prices of energy, and can also increase the consumption of renewable energy and even provide services to the grid. This is the main topic of today's webinar. And the Bamboo project, we are working in the pulp and paper sector, where different strategies and technologies are implemented to allow the operation of a whole paper plant as battery in the regional power grid of Germany. We will see, as I mentioned in detail, the demonstration in the next in this webinar. The third pillar is waste stream valorization, which includes technologies and processes to allow the upgrading and valorization of some waste stream which have a calorific value content and can be valorized as fuels in other processes on the company. In this case, we have two demonstrations in the steel sector and the mineral sector. In the steel sector, the concept is to valorize processed gas as fuel to increase the share of this fuel in these processes, reducing the consumption of natural gas. We are using two technologies in this demo. By simulations, we can predict the behavior of the combustion with these low calorific gases, and a flame monitoring system, which by images we can predict some malfunction in the combustion systems. Regarding the mineral sector, we are working with magnesium magnesite, in which a new multi-fuel low and aux burner has been developed. Together with simulation, are contributing to replace the coke, which was the original fuel, by biomass, reducing the consumption, in this case, as mentioned, pet coke, which have direct impact in the fossil fuel reduction. In this slide, we have collected some numbers about the potential impact based on the application of the bamboo technologies to the 1% of the energy intensive industries in Europe. In this case, steel and iron sector has a high weight in the industry of the European Union, so the numbers are really interesting and very important reduction in energy and energy consumption costs and CO2 emissions. In the rest of the demo sites, in the rest of the industry, sorry, we have also an important reduction. As Helen mentioned, this is the last webinar of the Bamboo series webinars. We have been recording all the webinars of the last week. So if you couldn't attend and you are interested in these webinars, you can check the website of the Bamboo project where you will find the presentations used and the YouTube channel of the project where we can see the recording of these sessions. Thank you again, everybody, for being connected today.
So thanks a lot, Jorge and Alvaro. Well, this is the last webinar of the series, but as we heard, we are nearing also the end of the Bamboo project. And I wanted to know a bit what you think about it. How did it go? What are the results? Have you learned any lessons? Let's wrap it up.
Okay, yes, we are now in the last 3 months of the project. We have a lot of results, but we are expecting some result of some demo sites. We encourage you to be connected with the project, with the dissemination activities of the project, especially with the February last event, the final event of the project. Until now, I think that we have faced a lot of issues during the project, like the pandemic, like change of strategies, energy contests. But at the end, I think the results we have obtained are good. We have obtained great results on expected results on energy reduction and pollutant emissions in the case of the Grecian sites. We have also good results in the part of the combustion. So I think that we are having a good contribution to the society with the project. As I mentioned, we have to face a lot of issues, change of scope of some parts, but at the end, we are getting great results.
We can't hear you, Selena.
Okay, yes, sorry, I was muted. Yes, that's great. Now, before getting into the topic of today's webinar, we should have another round of polls to understand the relationship of you, the audience, with the kind of technology we're going to talk about today. So this is about the first part of today's presentation. Industrial flexibility to you is in general the ability to adapt, the ability to react to customer wishes, the ability to get economic opportunities on energy markets, or the ability to change the energy demand quickly and efficiently. So just there is no wrong answer. What is it about according to you? We are going to talk about it anyway in a few moments. So, okay, for the 44% of you, it is the ability to change the energy demand quickly and efficiently. For 22% of you, it's in general the ability to adapt or the ability to get economic opportunities on energy markets. And for 11% of you, it's the ability to react to customer wishes. So we will discover it later. We should have another poll. What do you think is the biggest challenge for the pulp and paper sector? Is it high energy prices? Is that no technologies for decarbonization are available, or is it the reduction of product demand? I suppose since none of you is from the pulp and paper sector, it's going to be a bit of a guessing, but why not? Okay, so for most of you, almost yes, almost all of you, it's high energy prices, 67%, and for a third of our audience, it's the reduction of product demand. Nobody answered no technologies for decarbonization are available. So thank you all. Okay, now let's hear about this virtual battery model applied to a use case from the pulp and paper sector. Before I remind you that you can write your questions in the chat box at any time during the presentation. The first part is presented by Kilian Dickel, research assistant at Technische Universität Braunschweig. Kilian, the floor is yours.
Yeah, thank you, Selena. And I want to welcome you to the, first part of today's webinar about the the virtual battery model applied to use case in the pulp and paper sector. I will present the first part, and the second part, Sophie Knöttner from the Austrian Institute of Technology will take over. And I want to say special thanks to Stefan Puschnik, who helped us with the slides you can see today. At first, I will talk about the energy flexibility in general, as well as the pulp and paper sector in Germany. After that, I will talk a little bit of our special use case in the Bamboo project. And after that, Sophie Knöttner will talk over the optimization method we used during our research, as well as the conclusions. Let's start with the energy flexibility, with our motivation about energy flexibility and the pulp and paper sector. So as probably most of you know, the German electricity grid consists of a high share of volatile renewable energy. Already, we have around 55 gigawatts of wind onshore, as well as photovoltaics in our electricity grid. As I said, volatile energy, so it changes a little bit, and also an increasing share of offshore wind energy. There's the special case in Germany that we have in the northern part of Germany a lot of wind energy, of course, with the northern and the Baltic Sea, whilst in southern Germany we have a higher share of photovoltaic electricity in the grid. This means since we have a higher energy production in northern Germany, we need electricity distribution over long distances, so from northern Germany to southern Germany, which requires a substantial change in the electricity grid. At the moment, the grid in Germany uses the AC technology, like it's usually in all over Europe. You know about the 50 Hertz. And this has the problem that the transportation of energy over long distances comes with high loss in energy. On the other hand, whilst direct current transmission would be more efficient, in Germany there is a problem with the public acceptance of high voltage direct current transportation. So this means at this point in time, since the electricity share is already so high, we need to include the volatile renewable energy sources into our production system and use them locally. So the reliable generation, storage and distribution of electricity is crucial for the security of supply. This means we need to invent strategies to integrate regional renewable energy surpluses into our production and our electricity grids. Also, in the future, with an increasing share of renewable energy, operational changes from the industry are required in order to increase the share and penetration of renewables. What this means, I'll talk about right now. So here you can see on the left side the energy generation in 2020, already only from volatile renewable energy. So we are already at 110 to 120 gigawatts installed power. And as stated in the coalition agreement from the new legislation, this should increase to over 300 gigawatts in 2030 and to over 600 gigawatts in 2045. So this rapid increase of newly installed volatile renewable energy means that the production processes and production consumption needs to be adapted. When we see here on the left side the classic energy demand of a factory, we can see we have some phases of low energy demand, which are like night times or weekends. And when the production starts, we have like a high increase of our energy demand. On the other side, we have our on-site and grid energy with a high share of renewable energy. And of course, this, for example, a PV profile follows the solar radiation, which means we have a peak in electricity generation during the noon hours and lesser energy in the night times. When we now combine the energy demand of a factory with the grid energy or the energy generation due to renewable energy, we can see that it doesn't match quite well. So whilst the general shape looks okay in the first place, we can see we have phases with where the energy demand of our factory is too high, as well as some times where the energy demand of our factory is too low for our energy generation. This means we need to flexibilize our energy demand, which means that we want to effectively synchronize the energy demand of our industry with the volatile energy supply. There are a few technologies which we can use to do so. And this is also what we looked into during the Bamboo project. So to utilize flexibility potential of our industrial consumers and their given power plants on site, we need to consume regionally produced renewable energy. Since our demo site is in the southern parts of Germany, we looked in this research project into solar radiation or photovoltaic, but the concept can be applied to wind generation or every part of volatile energy as well. This also has the goal to support the stabilization of the power grid, whilst not needing as much costly infrastructure as we would need without the help of the German industry. This can be reached due to demand-side management. So there are a few concepts that can be applied to generate energy flexibility, which are, for example, peak clipping, valley filling, load shifting, energy efficiency overall, as well as a flexible load shape due to electrification of industrial processes. This only means that from a demand-side management perspective, we need to adapt whilst different means to the energy generation on site. Also, which is already shown in different German companies, the industrial on-site generation, mostly based on fossil fuels like gas, combined heat and power plant, or even during the gas crisis, oil plants, which get used more and more, can be partly or often even fully substituted by renewable energies generated on site or in the closer region. For this, we have different flexibility technologies which can be implemented on a short time scale and are relatively cheap in comparison to other technologies, which are on the one hand electrical and thermal storages, which are power to heat measures like heat pumps or electric boilers, as well as I stated earlier before, the integration of regional photovoltaics via, for example, a power purchase agreement. And another part which needs to be considered is the increasing consumer request of product with lesser carbon footprint. So for this example, less carbon intensive produced paper. So being more sustainable as a company whole and even just on a product scale. The flexibility approach we looked into during the Bamboo project aims for the reduction of carbon emissions for the production of 1 ton of paper. So in better inclusion of renewable and so less carbon intensive energy sources, as well as the balance of daily and seasonal fluctuations in energy generation from an on-site and a grid perspective. After this brief introduction about our motivation, I want to talk now about the use case during our pulp and paper production, as well as give you a brief overview about the concept of the virtual battery model. So let's start easily with the energy conversion chain of a pulp and paper sector. This should look familiar to most of you who work in the industry. On the first side, we have our production demand. We know this. This is like the energy grid was used for before. We have a demand, and depending on the demand, our energy generation increases or decreases. For paper production, we have steam, water, and electricity as energy sources. And on the other side from the conversion chain, of course, we have our energy supply, which consists of grid electricity, natural gas, as well as regional renewable energy via a power purchase agreement, or even on-site renewables, which needs to be integrated in our concept. The next step, whilst electricity can be used directly, we need to convert the energy to produce steam, hot water, and so on. For this, we have looked into technologies like an electric boiler or a steam-producing heat pump, as well as the classic heat-only boiler and the combined heater power plant, which work on natural gas and are already inside our paper factory. But since we want to flexibilize our energy demand, the next part, so now we could produce steam in the same rate as the production demands it, but what we want to look into are the energy storages as well. So classic energy storages would be like a heat store or a battery, which most of you probably are familiar as well. So this just roughly gives us the energy conversion chain of a paper factory, but it would probably look the same for a lot of industries. Next, I want to talk a little bit of the production process of a pulp and paper plant. So generally speaking, we have our fixed supply on the left side. We have fixed production capacities in the middle, overall fixed, so it's just inside this green box. And we have a prescribed annual production. So these are the boxes, we can't do anything about that. But now let's look into these boxes. For the fixed supply, we have in this example a wood supply A and B, which are different kinds of wood. And this is also fixed. We can't change anything about that. Next, this wood, of course, gets stored in a lumberyard. Here we have a storage, so we can already flexibilize a little bit about our production, since depending on the size of the lumberyard, we can store more or less wood from our fixed income. The next step in the process chain would be to ground our just delivered wood, as well as produce waste paper pulp. And here we have our first production plants as well as our first energy demands. So for the grounding machines, we have an electricity demand, which can be regulated depending on the rate of production. And for the waste paper pulp production, we have also heating demand. So in this case, hot steam. These production capacities give us ground wood as well as waste paper pulp, which are stored respectively. And again, here we have another storage, and depending on the size of our storages, we can increase or decrease our production here in the middle to a certain rate, and therefore also increase or decrease our electricity demand and our heating demand. So from the idea of a virtual battery model, since we can increase our production from our ground wood A, we have an increased demand of electricity, and our ground wood storage A gets filled. Now we have a time where we have less renewable energy in the grid, or energy for use as general. Then we can decrease the production of our ground wood machine and use our increased storage capacities to fill these gaps in production. So this gives, therefore comes the name virtual battery, since from a grid perspective, when we reduce our demand from our baseline, we get like, yeah, it looks like we bring back electricity to the grid, even though we just we stored the electricity in our intermediate product. Of course, with our ground wood, we still don't have final papers, so another production process comes in place. Again, with heating and an electricity demand. And again, since we have a prescribed annual production, but not like a production at the moment, we can flexibilize here again a little bit about our energy demands. When we combine our energy conversion chain with our production processes, we end up with something like this. Here you can see the base configuration of our virtual battery model. So the use case we started with at the beginning of the Bamboo project. On the left side, we have our energy supply, like the grid electricity as well as the natural gas grid. Then we have our on-site energy supply. This is what I've called energy conversion in the other slide. So here we have a gas and steam power plant, the CHP, as well as steam boilers. And after that, we have here called energy balancing. So the where the power and the heat supply get shifted or supplied to our production processes. And here is also where the demand from our production processes gets fulfilled. We have like our paper machines, our ground wood machine, which we know from the other slide just before, as well as an external heat consumption, which is just like local industry, also with demand of high temperature heat. What we can do now with the virtual battery model is like look into different cases. So like what happens when we include electricity via a power purchase agreement into our simulation, as well as let's say a steam producing heat pump. So now we have for the heat generation equivalency, we can still use natural gas for our heat generation, as well as electricity, like when we have a high share of the photovoltaic electricity, solar electricity, we can use this in combination with a steam producing heat pump to supply our heat as well as our energy or electricity, and so have a lower share or a lower carbon footprint for our product. When we combine all these methodologies together, we end up with our virtual battery model. So here you can see the production processes are considered as well as the energy utility flexibilities on site with our different storage technologies and our energy conversion. We have our production flexibilities like temporary shutdowns or load management or load shifting, as well as storages with the intermediate product. So as I've said before, like we can just increase our pulp production or our ground wood production and use this on a later point in time when the energy is less available. This also includes the local grid stability as well as the use of excess heat for the local consumers on site. And we gain flexibility due to existing assets as well as new assets which are considered. And the benefits of this are, of course, the integration of renewable energy as well as the increase of local grid stability. We have a certain production flexibility as well as the option to work cost optimized. So this is also a method we can optimize due to carbon footprints or due to the cost efficiency. But this is the part, so Knöppner will, after a brief poll, talk about.
Yes, thank you a lot, Kilian. So before giving the floor to Sophie, we have another round of polls introducing the second part of this presentation. We want to know if you have ever been involved with the method of mathematical optimization in industry. You may answer that you don't know anything about it, that you have just heard about it, that you considered it but did not apply it so far, or that you applied it already. So 42% of you heard about it. 25% consider it but did not apply it so far. And 17% either applied it already or do not know about it. Before going to the next poll, I wanted to, there was a question for Kilian. Is the concept of energy flexibility only relevant for the German/EU grid? Could you answer?
No, since we have an increase in renewable energy all over the world, so not only in Germany, but also in the other parts of the EU, as well as globally. The concepts of energy flexibility still, whilst Germany being like the first one to apply it in such a big scale for such an industry country, is relevant for all countries with a higher production share or even a higher share of renewable energy in their local electricity grid.
Okay, so let's go to the next poll. What do you think is most important in the energy transition process for energy-intensive industry? Technological progress, for example, photovoltaics or geothermal, smart tools to benefit from technology combinations, or financial support and subsidies? Okay, so 42% think that smart tools to benefit from technology combinations are most important in the energy transition process. 33% financial support and subsidies, and 25% have answered technological progress. I don't know if Sophie or Kilian want to comment on these results, or maybe in the previous polls. Any comments?
Maybe on the second one from my side.
Yeah.
Most important, I think there is no wrong or right answer. It's just interesting to see, what's the opinion of the audience, or maybe also the expectations. And well, for me, probably the easiest answer would have been all three of them. But sometimes it's good if you have to choose, and I'm lucky that majority chose the combinations, because that's something we will see in the second part, that combinations can help to increase flexibility and also renewable integration.
Good, good. So thank you everyone for your participation, and now let's go to the conclusion. Let's hear it from Sophie Knöckner, a research engineer at the Austrian Institute of Technology. So please, Sophie, the floor is yours.
Thank you very much, Selene. So yes, I'm happy that you are joining us this afternoon. I will now, in the second part of this presentation, dive a little deeper into the applied method of mathematical optimization. And yeah, this was already introduced in the poll question, the topic of mathematical optimization. And I will start with a short look what are the steps that are necessary to derive an optimization model and solve an optimization model for an industrial use case. So what you see here is more or less the workflow we had in the Bamboo project to set up the virtual battery, and we used a mathematical optimization model therefore. So what are the important steps? Step one is for sure to collect the information about the site. Typical approaches are interviews, a site visit, data acquisition and processing. All this happened in the Bamboo project, and actually this is the essential basis to set up an optimization model. In the next step, we translated the information we gathered in step one into a mathematical model, into mathematical equations. We have in mathematical optimization more or less four main components. First, there's the objective function. This is what you usually want to minimize when you optimize your model. So typically you have minimizing costs as objective or minimizing emissions. Today, here we will show results for minimization of costs, but for the use case, we will also do a minimization of emissions. The second main component of an optimization model are decision variables. Decision variables are that part of the model that are determined by the solver, which I will explain in step 3. So what are examples for such decision variables? For instance, a decision variable can be if a unit is integrated or not. So if a heat pump is integrated or not, how big this heat pump is, so what is the heating capacity, and also for new but existing units, what are the operation points in every time step of the model? So is it off, is it on, is it operated at full load, at part load, or somewhere in between? The third main component are constraints. Actually, these are equations used to express the technical characteristics. So we have ramping characteristics, on and offline characteristics. So for instance, a unit has to be offline for a certain time when it's shut down, but also the meeting of the supply and the demand is defined by those constraints. And the fourth main component, number 4, are parameters. What is expressed with parameters, for instance, investment costs. Another example are energy costs, but also the, in our case, the maximum installed capacity for the photovoltaic plant was defined by a parameter and could be varied. So this was the first step into translating the mathematical equations from the information we found. And the second part was we defined scenarios we wanted to calculate for the virtual battery we defined by the equations. A third essential step to solve the model is to use a solver. Actually, a solver is an algorithm that finds optimal values for the defined decision variables according to the defined objective, in our case, minimal costs. Here it is important to use a suitable and efficient solver for your formulation of the model. This task can be really time-consuming, but it can be repeated for a variation of parameters and settings in the model once the whole model is defined. Next slide, we see the characteristics and details of the derived model. As I said before, it's important to use an efficient solver for your formulation. So what is the method, the formulation we applied? We applied so-called mixed integer linear programming. What does it mean? It means that all our correlations, all our equations are linear, and that our decision variables are either continuous variables or integer variables. For instance, the integration of a heat pump, yes or no, this is typically a binary variable. The software we used is Python. We applied the Pyomo module, which is a module especially used for optimization tasks, and as a solver, the so-called Cplex solver, which is one of the 2 main solvers for those mixed integer linear programming formulations. The scope of our optimization was to find optimal design and operation for the system, design for the new units, such as heat pumps, operation for the existing units. We considered a period of 1 year and wanted to minimize the costs of 1 year. Therefore, we said we want to minimize total annual costs and annualize the investment costs in our objective function. In general, the model first had a temporal resolution of 1 hour. Here we found a big challenge. We found that it has long calculation periods. Therefore, we made the time step size adaptable. So also 8 hours would be possible, but we used 1, 4, and 6 hours so far and could find solutions for all those time steps. And you see a decreasing solution time when you increase the time step duration. A set of scenarios and variations in the model is in general possible for all main components I described before. So you can exchange objective functions, you can exchange decision variables, and also parameters and constraints. In our case, we varied for the results we will see in the following, mainly the parameters, but also the variables. So we said, okay, first we have our basic system, Kilian showed you before, and then we have another system where new decision variables occur for the integration of heat pump and photovoltaics. In general, we varied the integrated units and also the costs for the PPA integration, for the photovoltaic production, and for the heat pump investment. So we'll see 3 scenarios and results for those 3 scenarios. First, the basic scenario with no new units, then an addition with PV photovoltaics, and as a third scenario, additionally also the heat pump. Further potential variations are to include further units, for instance, electric boilers, but also storages, to include more regulatory frame conditions. Adaptation of paper amounts is also possible, so that the whole annual production is increased or lowered. And also further price variations, for instance, for electricity and natural gas from the grid, are possible. So I'll come back to this slide again before looking into the results. The first results we will see are for this configuration. So we have on the left the energy supply from the external grid, then the on-site energy provision, the balancing and calculation, and the production process. Here we have in general flexibility in the on-site energy supply and in the production process. Let's start with the on-site energy supply. What did we see? What did we see for the combined heat and power plant? We saw that the only use flexibility was within the ramping possibilities of this unit. So we didn't see any on and off switching. What are the reasons? The reasons is that this is a really efficient cogeneration unit. It can provide heat and electricity. And it is flexible because it has a rather good ramping ability, but we won't see any on or offline changes in the basic scenario. The heat-only boilers, which could supply steam instead of the combined heat and power plant, were not used in this scenario, so no flexibility was used from these units. What did we see for the production process? Here we saw 2 differences. First, production line A. Here we saw flexibility in single units. So more or less we had the groundwood preparation and the paper machine, and we saw that both of them were more or less operated flexibility to a higher extent or a little lower extent. But overall, the total energy consumption was rather constant through the operation phase. And this is due to economics. As in Germany, you have a power-related system charge. The optimization model tended to keep the overall consumption rather constant to get the best outcome with these power-related constraints. For production line B, in general, also both part units could be operated flexible, but here the annual amount led to operation close to the capacity limits, and therefore no flexibility was analyzed or found here for the basic scenario. So when we move to the next scenario, we look at the use case with the PPA and the heat pump again. So compared to before, we integrated first a photovoltaic power purchase agreement and then also a heat pump. What did we find for the integration of only a power purchase agreement? What were the frame conditions and the assumptions? The first frame condition was that we assumed a maximum power generation of 125 megawatt peak. And the modus was as produced. What does this mean? This means that the industrial site has to consume all of the produced electricity. So there is no 100% consumption in winter and 50% consumption in summer. It always has to be 100% of the produced electricity. We assume that this is not considered with investment costs, but the consumption is via the grid connection. So doesn't matter if the electricity is consumed from the electric grid or the power purchase agreement unit. The power charge fee I mentioned before has to be paid anyway. Compared to electricity, natural gas, and emission prices for 2019, we did 2 variations of the energy costs for the electricity from the PPA. The first calculation was with 40 euros per megawatt hour, and this is over the year pretty much the average the electricity from the grid had. So there were hours in winter when it was a little more expensive, and hours in summer where it was definitely less expensive than 40 euros per megawatt hour. With this price, we did not find any integration of the heat pump. So this was due to the fact that the drawback in summer was too big, because the electricity in summer, when the PV is able to produce a lot, is cheaper from the grid than the 40 euros, so no integration was found. Okay, in the next step, we set it to 0 to find what can be included as a maximum if there is no price for electricity. And here we found that of the 125 megawatt possible, only 40 megawatts was integrated. Again, here we see that the CHP I mentioned before is really efficient in production. And if we turn down the CHP in total, all the other units have to start, so the heat boilers, and there has to be more consumption from the grid. This is a reason why not the full power purchase agreement potential is exploited. In the next step, we'll edit the heat pump and we'll analyze those results too. So what are the main assumptions for the heat pump integration? Let's start with the excess heat on the source side of the heat pump. Here we assumed, we considered calculations and data collection that was done before in the Bamboo project, and saw that approximately 10 megawatts of wastewater with temperatures starting from 58 degrees Celsius could be used. And if we lower the temperature down to 30 degrees Celsius, we reach that amount of 10 megawatts. The waste heat amount is rather constant over the year, and therefore we assume that it's a constant provision of excess heat. Regarding the economics, we had again the price situation for electricity, natural gas, and emissions as it was in 2019. And we considered two capex of the high temperature heat pump system. First, with about 1,000 euros per kilowatt of heating power. There we found no integration with no capex. So the assumption that the heat pump already exists, we found a full usage of the excess heat potential, resulting in about 25 megawatt of heating power of the heat pump. What we also found is shown in the picture on the right side, the full load hours. We see that the CHP has a rather low amount of full load hours. Where does it come from? The CHP in that case is a little over-dimensioned. So it's operated close to the minimum part load all over the time, while the heat pump is, when it's operated close to the full load. The photovoltaic is, as before, integrated as produced, so all of the produced photovoltaic is used in the production process. And what we found here too, what was really interesting for me, is that when we included the heat pump, also a higher share of photovoltaic could be included. So compared to before, where 40 megawatts was included, here we found approximately 50 megawatts. I'll give a short overview about the single units and components in the model. So what did we see with the PPA and heat pump integration for the overall electricity consumption? In general, we saw much more fluctuations in the overall consumption than in the two scenarios before. For the combined heat and power plant, we saw that the flexibility of ramping was used, and also on and offline states were used, which has not been shown before in any of the scenarios 1 or 2. So within the ramping limits, it was operated flexible, and especially in summer during the days, we saw that it was shut down for a couple of hours. The heat-only boilers, therefore, were turned on, especially in summer, to a small extent to allow the CHP total shutdown. And the photovoltaic was integrated as produced, so here was no flexibility used. Actually, the photovoltaics unit, when it's considered as produced unit, cannot be operated flexible, but a higher integration was shown with the heat pump integration. So this was my last slide for the result and method presentation, and I will make some conclusions in the end. I'll start with the conclusions regarding the use case. What did we find? One finding was that the high capacity usage in the production system. So the amount of paper that we wanted to produce was close to the full load or full potential, limited the flexibility. So if less paper needs to be produced, also the flexibility in the production process could be used more. A second finding was that existing plants can limit the flexibility. This is what we found for the CHP. If the design is, as it is here, a little over capacity, so the CHP is dimensioned a little too big for the overall process, the flexibility limits are rather small, so I cannot take the full potential. And the third important finding was that technology combinations in the energy supply, as we saw it in the last scenario for heat pumps and the PPA, seem to be promising to include more flexibility and include and integrate more renewable fluctuating generation in industrial processes. The second slide for the conclusions focus on how suitable is the method of mathematical optimization for the concept of a virtual battery in this sector. So we have some positive findings for that. What are the positive findings? In our opinion, the specifications we wanted to include, the frame conditions, the power purchase agreements, the energy balancing, all of them can be formulated with mixed integer linear programming. The method is also really suitable for scenario calculation, as you can calculate iteratively. And in our opinion, it can be repeated for other sites and sectors, but it needs adaptation. So it's not the case that I can replace the sector and then calculate 5 minutes later again. I need adaptations, but it seems promising that we can apply it in other sectors too. A neutral finding is that the data preparation and the setup of the system have a really, really strong dependence on the information and data exchange with the industrial partner. So the quality of the model strongly depends on the information exchange. In our project, we found a really good exchange, but if the exchange is not as good, or if the data amount and data background is not as good, it can be a drawback of this method. And the negative finding for the model we applied here, or for the model we defined here, is that we found really long calculation times. So to be more efficient in calculation, we need some adaptations in the model. We found improvement potential and also possible measures, but did not apply this so far. So here, especially in our case with the heat boilers, which have really, really similar capacities, the calculation can increase a lot, and there adaptations will be needed to make it more efficient and faster. Thanks from our side at this time in the webinar. Thanks for joining us and your interest in our work. And I think both of us, Kilian and me, will be happy to answer further questions.
Yeah, of course.
Thanks a lot, Sophie. Yes, we have a lot of time. You were very efficient. So if someone wants to send their questions through the chat box, you can do so. I have a few questions for you both. First is, how market ready is this technology?
The heat pump?
Yes.
High temperature heat pump, yeah. Well, what we included here, the technology of steam generating heat pumps. I would say there are several suppliers currently. And the technology of the steam generating heat pump is in an advanced demo and pilot scale, I would say. So there are first industrial plants buying steam generating heat pumps and implementing them, but it's not that there is a huge range of demo projects and pilot sites. So if you use the technology readiness level, I would say somewhere between 7 and 9. Also, we had it last week in the webinar that there are demo projects, but not at a big scale already implementation in the industry. Where the market or the market readiness is higher is the technology of mechanical vapor recompression, also often referred to as open loop heat pumps. And this is the case when I have steam at a lower pressure and want to bring it up to a higher pressure. So use the steam directly as a working fluid of the heat pump. And this technology is market ready. There are several suppliers and several demo projects. So I would say depends. If you really want just have a closed heat pump or open loop heat pump, we are somewhere between technology readiness level 7 to 9 and 9 for the open loop heat pumps.
Yes, as you said last week, we talked about heat pumps. So if some of you are interested, I really suggest that you have a look at the video that is on the Bamboo website. And for any other technologies, please do so. In which sectors can this technology be applied other than the pulp and paper sector? Since we have seen that most of our audience is not from that sector today, at least.
Well, in the Bamboo project, we discussed, for instance, usage of this method for the steel industry and what it would need. And we found that with enough information provided, so also temporal resolved information, there is a huge potential. And I would say especially the energy intensive sector usually has good measurement data and a good databases. So it makes it easier to apply such a method to this sector. But also we found in our other work that mathematical optimization is promising, for instance, for small scale sites in the food sector. So I would say in general, there are several sectors: chemistry, food sector, wood sector, iron and steel, non-ferrous metals, and the quality of the model really depends on the databases that is available and the readiness of the industrial partner to provide information and show you the interfaces and the connections in their processes and sites. But there's no sector I would generally exclude. Sorry, Kilian, please.
No problem. Yeah, in my experience, the concept of the virtual battery model, since we look into the intermediate product as a storage technology, is really suitable for every industry which has like high intensive processes and then get an intermediate product. So these production steps can be used to generate flexibility from the energy demand side. But on the other hand, considering the electricity and heat storages, as well as the integration of renewable energy, which is also part of the virtual battery model, this can be applied to all industry. So the effectiveness of the virtual battery model depends a little bit on the production process itself, but theoretical from a construct and from the idea behind the virtual battery model is applicable to all industry, in my opinion.
Yeah, maybe I can. This is a really, really important point, and I would like to add here something. Kilian said that depending on the production process, so the frame conditions and the background in the past motivated efficiency increase in industry, and for instance, in the paper sector, high full load hours. So the more constant the load consumption, the electricity consumption is, the better it is from an economic perspective. This was really suitable as long as we had a big share of baseload power plants in the electricity system, which operated best in one operation point, and ramping was not efficient. But the more fluctuating renewable generation we have in the electricity system, the better flexible consumption would be. So here we have two conflicting parts. We have an increasing fluctuation and increasing fluctuating prices in the electricity demand, but still regulatory frame conditions motivating a constant consumption. So I think here is also potential if the frame conditions are adapted, the regulatories.
Thank you, Sophie. I would also like to inform the audience that the presentation of this of today's presentation is available via the Bamboo project website in the resources section. So you can there's the link in the chat box if you are interested. Another question is the concept of that's a question you already answered. What could be a financial incentive to flexibilize the energy demand?
Okay, yeah, thank you for the question. I'll answer that. Energy flexibility right now, since it can result in an increase of electricity consumption in a certain time, it is sometimes counterproductive from a financial standpoint, because in Germany there is this fee called power surcharge fee, which means you need to pay for the highest load in a 50-minute window per year. So when we have like little peaks in our energy consumption, we need to pay extra. On the other hand, right now, the energy flexibility can also be used just to decrease our power peaks. For example, when we have a good demand side management, we can just manage it that not all machines at the same time go into the ramp up phase. So it gets staged a little bit, and then we have like a flatter load profile, or even use on-site batteries for this peak clipping, as I've said before. On the other hand, there are, in Germany at least, more and more companies who get their electricity prices from the day-ahead market. So they don't get a constant electricity price by the electricity provider, but just get the fluctuating market prices. So this is also on a larger time scale, not only a 50-minute window, but more like, as I said, day-ahead market. They work on this fluctuating prices, so then they have an incentive to use energy when it's cheap and have energy in store when it gets more expensive. So there is already, because of these peak surcharges that are already in place, an incentive, as well as when transitioning to the day-ahead market.
Okay. What are factors to facilitate or speed up integration of high temperature heat pumps? Sophie?
So yeah, the integration of high temperature heat pumps, I think there are more levels or more contributions to speed up this integration. Maybe let's think about the last poll question. Here we had the answers: it needs efficient technologies, it needs combinations, and it needs financial support. And I think here more or less all three answers are right. I think it needs an progress in the demonstration and pilot phase of such plans to learn more, to maybe decrease the investment costs a little further. I think from the current perspective, it also needs some financial incentives at least to decarbonize and integrate such technologies. And I think a big booster of heat pump integration could be efficiency optimization in terms of finding the ideal temperatures of the process. What we see now often, not mainly in the pulp and paper sector, but I think it's a finding you can have over all sectors, is that the temperatures provided, the steam temperatures provided, are rather high, although the process itself needs lower flow temperatures. So especially in the food industry, often steam with 150 or 120 degrees Celsius is provided, although hot water would be sufficient, or steam with 150 degrees is provided, and then in the process itself brought down to 120 degrees. So if those optimization potentials, those efficiency potentials can be lifted, I think the integration of high temperature heat pumps will be easier in the future too. So three answers: more demo, more pilot projects to understand the technology even better, more financial incentives and regulatory incentives, and adaptation of the processes will help too and will facilitate the integration.
Okay. What are the typical calculation times for the optimization model?
Here, several hours. So could be 3 hours. Depends a little on the parameters. When there are solution branches that occur to be good branches really soon, then the model solves a little faster. So then we are in the optimization time range of about 3 to 4 hours, can be up to 6 to 8 hours, and for the 1 hour resolution, it's even longer. Yeah, so this is really a big challenge. And here, especially in our model, one challenge is that the heat-only boilers are really close in their capacities, for instance. So all of them are more or less equally good if they are needed for the solver. And when the solver needs to integrate the heat-only boilers because he wants to shut down the CHP, for instance, there are 3 and 3 more or less equally good solutions, and then it takes really long to find a solution. So as I mentioned before, one measure to increase, for instance, the speed could be to summarize those heat-only boilers into 1 or 2 units only. One measure we already said was the adaptation of the time step duration from 1 hour to 4 or 6 hours. Yeah, these are two examples how it could be faster.
Okay, so for now there are no more questions. There's still a few minutes if someone wants to ask for something. Otherwise, our webinar and our series ends here. But if you still have questions after the webinar, maybe you forgot or anything, you can still reach out to the key speakers. You will find their emails on the presentation available online in the Bamboo Project website, always in the resources sections. And of course, you can rewatch the previous webinars on the Bamboo YouTube page. As I said, you will receive the link to today's webinar in the following days in your email. We finished early. I don't know if our panelists want to say something as a last sentence to close. Maybe Jorge to close this series, since it's the last time we see each other.
Just to thank everybody, panelists, organizers, you, Selene, as moderator. I think that we have performed an interesting series of webinars. I hope everybody can extract something from them. And as I mentioned before, I encourage you to follow the final results of the project, stay connected, since we are going to make a final event during the month of February, where we can explain better the results and everything about the project. So thank you again.
Thank you, Jorge. This was very useful. So thank you again, everyone, panelists and attendees. And I think all I have to do is wish you a good afternoon and goodbye.
Yeah, thank you, Selena. Thank you, Jorge. Goodbye. Thank you, Sophie,
Goodbye.
for helping me with the presentation and the panel. And I wish you a nice week.
Same from me. Thanks for joining today.